let's go over some of this stuff and hint at how you get some of these results. So we already figured out that the expected value of a binomial random variable with parameters n and p is n times p. It is the sample sum of the numbers on the tickets that you get if you draw independently with replacement from a 0, 1 box that has a fraction p of tickets labeled 1, and you draw a little n times. Okay? Expected value of a geometric random variable. What's a geometric? Okay, so you're drawing from a 0, 1 box with replacement independently until the first time you see a ticket labeled 1. All right. Why does it make sense for the expected value to be 1 over p? So I'll give you a heuristic, and then I'll show you the proof briefly because you really don't want to see it. Heuristic is you get, if there's p tickets labeled 1, then every time you draw, you get sort of, there's p successes per draw. Does that make sense? You get sort of a fraction p tickets labeled 1 per draw on average. And so if you get p successes per draw, then how many draws per success are there? 1 over p, loosely speaking. So on average, how many times would you have to draw to get 1 success? On average, 1 over p. That's a loose heuristic. It's not completely accurate, but the proof that that's the expected value is a little longer. So you don't want to know that. You don't have to know that. Okay, but let's assume that we take this now as given, that the expected value of a geometric random variable with parameter p is 1 over p. From that, we can actually derive the fact that the expected value of a negative binomial random variable with parameters p and r is r over p. So let's reason that out, because this reasoning is actually helpful. Right. Remind me, what kind of thing has a negative binomial distribution? Okay, so we've got a 0, 1 box, right? Fraction p tickets labeled 1 in the box. We draw with replacement until the rth time we get a ticket labeled 1. Okay. Let's think of that as occurring in stages. We draw until the first time we get a ticket labeled 1. Then we draw until the next time we get a ticket labeled 1. Then we draw until the next time we get a ticket labeled 1, until we've done that r times. Okay? What's the distribution of the number of times I have to draw until I get the first ticket labeled 1? It's geometric, right? Now, starting there, what's the distribution of the number of times I have to draw until I get another ticket labeled 1? It's again geometric, right? I'm waiting from then until the first time I get a ticket labeled 1. And then once that's happened, I'm waiting from there until the first time I get a ticket labeled 1. And I have to do that a total of r times. So I could actually write a negative binomial random variable as the sum of r geometric random variables. So if we have x1, x2, so forth on up to xr, if these all independent random variables with the geometric distribution with parameter p, then if we define x to be x1 plus xr, the distribution of x is negative binomial with parameters r and p. Okay? I wait until the first time, and then I wait until the second time, and then I wait until the third time. Each time I'm drawing with replacement from the same box of tickets, same fraction P of tickets labeled 1. Everything is independent, right? So I can think of waiting for the 7th ticket labeled 1 as waiting for the first ticket labeled 1 and then starting over, and waiting for the first ticket labeled 1 and then starting over, and doing that 7 times. Okay, so the distribution of the sum of R independent geometrics is a negative binomial with parameters R and P. Okay, now we had that little rule that says the expected value of a sum is the sum of the expected values. What's the expected value of this geometric random variable? We've sort of said it's 1 over P without proving it. Yeah? The expected value of this one is 1 over P, et cetera, and the expected value of this one is 1 over P. So what's the expected value of their sum? R over P. Expected value of their sum is the sum of their expected values. 1 over P, 1 over P, 1 over P, 1 over P. That adds up to R over P. So knowing this, it's easy to prove this. Okay. Hypergeometric, we already did. Again, it's draws, in this case, without replacement from a box of numbered tickets. The average of the tickets in the box, the labels on the tickets in the box, is G over N. That's the fraction of tickets labeled 1 in the box. In general, if we draw little n times with or without replacement from a box of numbered tickets and add the results that we see, that sample sum, the expected value of the sample sum is n times the average of labels on the tickets in the box. The expected value of the sample mean is this divided by n, which is just the average of the labels on the tickets in the box. Of course, if we're drawing without replacement, we can't draw more times than there are tickets in the box.